This is a basic program running on a TRS-80 Color Computer. It's using the high-resolution graphics screen. But something strange is going on. This graphics mode is documented as having only two colors, black and white. So where did that reddish orange and blue come from? Soon I'll show how I did this, and if you don't already know the trick, it's weird. When I was a kid, I discovered these perplexing colors when I was writing my own basic games. I didn't write these, but they took full advantage of these undocumented colors. Does this look black and white to you? And then there's the other mystery. Hit the reset button or power the CoCo off and the reddish orange and blue colors might swap. If these extra colors are intentional, then why did the documentation gaslight us? And why would they force you to hit the reset button to switch the colors around? But then again, if they were accidental, how is it that they are so easy and clear to generate? These questions plagued my young mind. Back then there was no internet to look up information, no YouTube videos with extremely good-looking hosts to explain things. But that all changes now. Join me on this journey as I make sense of everything that confused me back then. We will go over the key concepts in NTSC Color, some early microcomputer history featuring the pioneering Apple II, and illustrate exactly what's going on step by step. In the process, I encounter a third question I didn't even know I had, and the answer kind of blew my mind. This is the basic program that made those rectangles in different colors, even though they're all supposed to be white. This line sets up the graphics mode. 4 means to use the highest resolution graphics mode, and this one sets up the color set to be black and white, and this clears it all to black. And here it is, the line that says that all drawing we should be doing should be in white. This block draws that white rectangle on the left side. It draws it as a series of vertical lines. We loop the x-coordinates to go from 10 to 75, and for each of those, we draw a vertical line from y-coordinate 50 down to y-coordinate 141. So it's no surprise this is going to make a white rectangle. The middle rectangle is over here, and it's basically the same thing. The x-coordinates are shifted over a bit so it'll show up in the middle, but this is the key. Step 2 makes sure that x goes up by 2 each time instead of by 1. And that means we're only going to be looking at even x-coordinates. We're going to start at 96, then go to 98, then go to 100, then 102. So we would expect to see zebra stripes. The black background mixed with these white vertical stripes. But instead, we get that red-orange color. And finally on the right side, the exact same trick, except we're doing odd pixels instead of even. Once again, instead of getting the zebra stripes we'd expect, we get color, and in this case, blue. So from the programmer's perspective, there really are only two colors, black and white. The extra colors we're seeing are an unintentional, even undesirable side effect of how color TVs work, known as color artifacts. These were indeed purposely exploited by the CoCo as well as other computers at the time. But for whatever reason, this effect was not included in the CoCo documentation. Perhaps they figured this was really just an expert professional developer type of feature and didn't want to burden us lowly basic developers with its existence. So let's dive into TV signals. We will specifically be discussing the standard set forth by NTSC, popular in North America and parts of Asia. Different regions had different standards. So for example, if you lived in the UK and your CoCo or one of its cousins like the Dragon used a PAL system like PAL-I, rather than seeing the NTSC artifact colors, you'd see the original black and white image generated by the software. This is not to say that NTSC was the only standard that had artifact colors, but it was particularly cheap and easy to take advantage of color artifact colors with NTSC. In order to understand NTSC color artifacts, we need to understand NTSC color. But that requires knowledge of how the original NTSC black and white signal was encoded. And luckily, it's really simple. Old black and white TVs generate an image by scanning an electron gun in horizontal lines, left to right, starting at the top of the screen and moving down to the bottom. This motion across the entire screen occurs 60 times a second. The electrons are aimed at phosphors coating the screen, which glow when hit. So how does this result in recognizable images? A TV needs two pieces of information. First, it needs brightness information, which is sent via a luma signal, also called Y. Luma is sent as a change in voltage over time. The higher the voltage, the greater the intensity of the electron beam, and the brighter the phosphors glow at that point in time. Here's what the horizontal line traced out from this luma signal might look like. Note how peaks in luma correspond to those small white blocks on the screen. Keep in mind that this is not to scale, everything is exaggerated just to make things more clear. Each horizontal line can have its own areas of brightness and darkness. Different peaks in luma result in different areas along that line becoming bright. Stack 525 of these lines from top to bottom of the screen and you get a complete frame of video. The TV needs a second piece of information to help it synchronize the motion of the electron gun. This is a horizontal sync pulse. Dropping the voltage for this short interval tells the TV it's time to move its beam all the way back to the left to prepare for the next horizontal line. A similar vertical sync pulse forces the TV to rewind its beam back up to the top of the screen after each field has been sent. These pulses are part of Y, the very same signal that transmits luma. So this one signal contains all the information that a black and white TV needs to display any video at all. Incredible! When it comes to NTSC color, the thing to realize is it had to be compatible with black and white TVs. If the advent of color TVs bricked everyone's old TV, Nielsen ratings would go way down. So how do you design a new transmission standard that old black and white TVs would faithfully convert to a black and white image, but new color TVs would figure out how to make a full color image? The answer is obvious.
Quadrature amplitude modulation.
Don't worry, it's exactly as complicated as it sounds. But luckily, we only need to understand the basics. We keep that Y signal, but we compose onto it color information called chroma. If you've heard the term composite video, this is it. The luma signal continues to tell the TV how brightness should change as we scan through each horizontal line. Meanwhile, the chroma signal tells the TV how the color's hue and saturation should change as we scan through each horizontal line. The hue describes the color itself as determined by the wavelength of light. The saturation describes the intensity or purity of the color, ranging from some shade of gray all the way up to the full color itself. The interesting thing about the chroma signal is that it always maintains the exact same frequency, 3.579545 MHz. So to convey hue and saturation, the chroma signal can't change its frequency. Instead, it uses phase and amplitude. Phase is a measure in degrees of where a cycle begins within the wave, relative to some reference point. Phase ranges from 0 degrees on up until it wraps back around at 360 degrees. In this diagram, the three peaks are changing their phase at different speeds. The peak on the right is changing phase faster than the other two, and if you look at the corresponding block on the screen, it's changing its hue faster than the other two. You can use this handy-dandy color wheel to convert between phase and hue. You can see how the change in phase results in a different color on the screen. And as the amplitude or height of the chroma signal changes, the saturation changes. The taller the wave, the greater the saturation. You may have noticed that I glossed over one important detail. I said that hue is encoded as a difference in phase between the chroma signal and some other baseline. But what baseline? Excellent question, I'm glad you asked. Have you ever been to a concert and the band leader tries to get the audience involved by telling them to clap to the beat? The leader claps, the audience catches on, and then the leader stops. But the audience keeps on going. The same kind of thing happens with the TV signal. First, as usual, the horizontal sync pulse is sent. Then we add several cycles of a color burst signal. This is the band leader clapping, teaching the TV the beat. And the beat is fast, 3.579545 MHz, the same frequency as the chroma signal. Then the color burst just stops. But it's enough for the TV to keep on clapping, and that is the reference signal it uses. Once the chroma signal starts, the TV compares the phase of chroma with the phase of this reference signal. The difference determines the hue. So now the fun part. What is it about this design that leads to color glitches? The problems arise when the TV decodes this signal back into its constituent parts, separating luma from chroma. First, what if chroma gets misinterpreted as luma? This can cause dot crawl, or cross-luminance, where a sudden change in color, like the edges of these red letters, gets misinterpreted as a shimmering luma change. This actually looks like an accident, not intentional. But this is not the kind of glitch that the CoCo exploits for its high-resolution black and white graphics screen. Instead, it relies on the reverse problem. What happens when luma gets misinterpreted as chroma? Consider this black and white screen, where we wish to represent pixels so small that luma goes up and down very quickly. In other words, the luma frequency gets very high. So high, in fact, that luma becomes indistinguishable from a valid chroma signal. Remember, the chroma frequency is always 3.579545 MHz. If luma horns in on that frequency, the TV will misinterpret the brightness changes as a valid chroma signal and will generate color as a result. Luma is impersonating chroma. The hue of the color is determined by the phase of the chroma signal, or whatever the TV thinks is the chroma signal, in this case luma. And we can control the phase of luma by shifting the pixels by tiny amounts. In effect, we're generating color not with chroma, but with the location of tiny white pixels. This considerably simplifies a computer's video display hardware, because now all it needs to produce is a luma, and it can do that with a simple digital square wave. And that is color artifacting, producing color not by chroma, but by luma. TVs shouldn't do this. This is a bug. This was a known bug. In fact, if you were to watch black and white content on your CRT color TV, it would likely generate these weird color artifacts, and it would not look right. Except, it actually looked just fine. Because color TVs implemented
the color killer.
Circuitry that would turn off all color processing if it received a black and white only signal. But how would the TV know that the signal was only supposed to be black and white? No color burst. So, no color burst, no color processing, pure black and white image. So how did early computers get around this? Send a perfectly crafted black and white luma signal with the color burst signal at the beginning. Done! Many of the sources I found credit Steve Wozniak as the first person to exploit NTSC color artifacts in a computer, with his Apple II line being the first computers to implement this approach. In fact, the only color you'll ever find on the Apple IIs is via artifacting, as the Apple IIs do not generate a chroma signal at all. This is remarkable given the many colors that Wozniak's 1979 patent describes how to generate in great detail. Going back even further, this interview with Alan Alcorn, who you may recognize as the developer of the original coin-operated Pong game, discusses the home version of Pong he'd also worked on, which used artifact colors to simply change color from the left side of the screen to the right. When Wozniak was designing the Apple II, Alcorn explained this technique to him. So apparently the seed of this idea of color artifacting actually originated with Alcorn. Or did it? And this is where my mind got blown. How did Alcorn discover color artifacting? He worked at TV repair shops in the 1960s, where they used color bar generators for testing color TVs. Normally, these would generate proper luma and chroma signals, but he came across one such test he called cheap and sleazy. It worked by simply generating a steady signal at slightly under the chroma frequency. So the signal looked like it was at the chroma frequency, but constantly shifting its phase by tiny amounts, totaling 360 degrees from left to right. Just think about this for a second. This color bar test did not generate a chroma signal at the proper frequency, at one phase for one bar, moving on to another phase for another bar, and so on. Instead, it sent one unchanging signal at a slightly wrong frequency, forcing the TV to do the hard work of interpreting the color changes itself. Laziness truly is the mother of invention. Later, when working on Atari's first Home Pong console, Alcorn used the same sleazy technique, where the colors simply changed from the left side to the right side of the screen, apparently just so that they could put the word color on the box. Later, Alcorn relayed this trick to Wozniak, who then developed it into a more extensible and programmable use of NTSC artifacting for his Apple II. By the way, I also came across this patent by Wozniak for an automatic shoelace tying machine. But it was a different Wozniak. Where was I again? Right, okay, so we now have all the steps we need for exploiting NTSC color artifacts. Send a color burst signal for each horizontal line, even though you will not be sending an actual chroma signal for any line, because you're sneaky. Ensure your pixels are small enough such that the luma generated by patterns of dark and light pixels appear in a frequency close to 3.579545 MHz. And ensure your pixel locations on the screen will cause the luma signal to phase shift from that color burst signal you sent to predictable degrees that result in the color you want. Easy peasy, lemon to the squeezy, and we're all done. Except for that one question about the reset button sometimes swapping the colors around. Games that used this high-resolution mode often started up with a screen that asked you to repeatedly hit reset until the right color was shown. Sometimes you would have to hit the reset button a whole lot of times before the desired color would finally show up. To make sense of this, we turn to the hardware design of the TRS-80 Color Computer. The main work is done by this chip, the VDG. It reads the video RAM and generates the luma signal, as well as two intermediate color signals. Those three signals then enter this chip, the RF modulator. Its job is to send all of the TV-compatible signals we've discussed, luma, chroma, and color burst, and modulate them to channel 3 or 4. The VDG's datasheet has this one rather vague statement. The VDG may power up using either the rising or falling edge of the clock. The clock it's talking about is the CoCo's master oscillator, which resides in a third chip, the SAM. The consequences of this uncertainty about powering up at either the rising or falling edge of the clock only make sense when you understand these two facts. First, the master oscillator connects to both the VDG and RF modulator independently. Second, the VDG uses that clock to generate luma, but the RF modulator uses the clock to generate color burst. And this is exactly how things get out of sync. On the one hand, the RF modulator generates the color burst directly from the clock. On the other hand, the VDG generates its luma in reference to either the falling or rising edge of the clock, which are 180 degrees apart. And the hue is determined by comparing these two signals. Since the luma might be shifted by 180 degrees, When the TV compares luma and color burst to determine the hue, it might calculate a difference that shifted an additional 180 degrees. And 180 degrees is exactly the phase difference you'd see between the reddish-orange and blue artifact colors that swap randomly each time you reset the CoCo. Case closed. It's worth mentioning that the CoCo 3 solved this problem. Its upgraded video hardware ensures it always starts on the same clock edge. You can even change which clock edge manually by pressing a key for compatibility with older CoCo 2 software. And there you have it. From a cheap and sleazy TV test color bar generator, to the official Home Pong console, to the Apple II and beyond. Send a color burst signal to disable the color killer, and then send the black and white only luma signal with pixels so small that its frequency reaches 3.579545 MHz, and the position of those pixels on the screen will then result in specific reliable colors without the need to manufacture a chroma signal. Reliable, that is, except for any phase difference between color burst and luma, caused by the hardware that generates those waves using an unreliable position on the oscillator from which to base one of those signals. Check the description for plenty of links if you would like to explore further. As always, thank you for watching. But this is not the kind of glitch that the CoCo exploits for its high-resolution graphics black and white screen. No, my gosh. But this is not the kind of glitch that the CoCo exploits for its high-resolution that old black and white TVs would still faithfully convert to an old black and white Remember, the chroma frequency is always 9. Jeez Louise. The extra colors we're seeing are a side effect, even an unintentional. Oh my god. If these extra colors are intentional, then why did they... How did Alcorn discover Carter...